Okay, you're live. You can go ahead. Thank you.
Okay. Hello, everyone. Welcome to this week's seminar. Today's speaker is Alexander Eggemeier. He did a PhD in Sussex and New York University. Then he did the first postdoc in Durham in the UK. And now he's working on Bonn University or Bonn Institute in Germany. He's an expert in the large-scale structure of the universe and now is an active member of the Euclid consortium or mission. And today he's going to talk about cosmological constraints from 2- and 3-point galaxy clustering. So the floor is yours.
Okay, thanks very much for the nice introduction and for having me here. I've been here already the whole week visiting Martin and his group, and it's been a really nice time and a nice change of weather, by the way, compared to Bonn. So I'm very happy. So the idea of this talk is going to be that I will begin by telling you or giving you a bit of an overview of how we extract cosmological constraints from galaxy survey data. And then I will particularly emphasize why it might be a good idea to use a combination of 2- and 3-point statistics. I will explain what I mean by that. And finally, I will end on a discussion that tries to get across why it's really important or crucial even to model these statistics very well to really profit from this 3-point information in the large-scale structure. So let's get started explaining what we actually measure from these galaxy surveys. And here, what you see here, this is an old galaxy survey. This is from the BOSS collaboration, showing different points here. Each point in this plot is a galaxy that has been observed as a function of redshift, right, going out to about redshift of 0.7. And you see the different samples that were collected in BOSS. In black, you see the BOSS CMAS sample. In red, underlying here, a bit lower redshift, you see the DESI sample. And in the center, very close to us, is the main galaxy sample of the ICE survey. And so in order to extract information from that, we want to understand how these different galaxies are clustered, right? And the simplest way to do that is to count pairs of galaxies. And so I would pick a galaxy and I fix the scale, and then I'm asking what's the probability of finding another galaxy at that distance from the first one. And this is what we call the 2-point correlation function, right? So we count really the probabilities of excess number of pairs compared to completely random distribution of galaxies. And this is this probability or this correlation function you can also write as this correlation between two densities. This is what I'm writing here. As delta, where delta is the density contrast, so the difference in density from the average in the universe. And you can correlate these two densities at two different positions, right? And we can define a similar statistic in Fourier space. This is called the power spectrum. In this case, it's a correlation of the density field in Fourier space, where now we're correlating this thing at two different wave modes, K1 and K2. This gives the power spectrum. And so how do we extract information from measurements of this 2-point correlation function of the power spectrum? Here you see such a measurement. This is showing the 2-point correlation function as a function of the pair separation scale transverse to the line of sight. So transverse to the line that we are looking at, right? So here, and as a function parallel to the line of sight. And there are two main ways of using these measurements to understand our cosmology. The first one is by detecting a particular feature that is called baryon acoustic oscillations, or BAOs, which appears as a slight bump in this correlation function, which signifies there's an increased probability of finding pairs at a particular scale. And this probes the geometry of the universe. The second main way of extracting information are so-called redshift-space distortions. which appears as a sort of squashing of this correlation function along the line of sight. And this is a probe of how quickly structures are growing in the universe. And I will go into a little bit more detail now how we use these two probes. Right, first probing geometry. Right, so what we fundamentally measure in a galaxy survey are not the actual positions of the galaxies, but what we are measuring are redshifts and angle sky. And so the first step is typically we have to convert these redshifts and angles into co-moving distance scales. And for that, you already have to assume a cosmological model, right? So along the line of sight, we can convert differences in redshift using the Hubble rate to get a distance scale. And transverse to the line of sight, we make use of the angular diameter distance. Right? And so specifying the Hubble rate and the angular diameter distance requires the assumption of a cosmological model, right? So we need to make a fiducial choice. So how do we know whether we made the correct fiducial choice, right? We don't know what the true underlying cosmology is. And to figure that out, you need to know, or we can make use of a known distance scale. Okay, and this distance scale is provided by this position of the BAO peak that I mentioned earlier. Right, so what you do is you measure this two-point correlation function. You see where is the peak, where does the peak appear in that two-point correlation function, and then you compare the position with this known distance scale of the BAO. And if you made a wrong choice in the fiducial cosmology, then there will be shifts in this or distortions in the position along the line of sight and transverse to the line of sight, which are quantified by something that we call Alcock-Bashinsky parameters. Right, and so by measuring these two parameters, we can then constrain the actual cosmology. And here are some past measurements that have been done on the Hubble rate as a function of redshift, right, using the BOSS survey that I showed earlier. So here this is from the low Z and CMAS samples and quasars and from Lyman Parker Forest. And in black here, this is the prediction assuming a lambda CDM universe from Planck, right? And you can see that this is all in very good agreement, except this one data point here at low redshift that is coming from supernovae, which we know is the well-known tension between in the measurements of the expansion rate. And this is going to get very exciting very soon. With data that is coming very soon from DESI, the Dark Energy Spectroscopic Instrument, and also from the Euclid satellite. And what you see here, this is a forecast that was done for DESI, and you can see how it improves dramatically over what BOSS has done in the past, covering a much wider redshift range and decreasing the statistical uncertainties. So this will be a very precise test of our cosmological models. And I think very soon I can probably replace this forecast plot with actual measurements. So it's super exciting, and I'm quite looking forward to see what comes out. I'm working in Euclid. Euclid is fairly comparable to DESI in the size of these error bars. It's going to do a little bit better on this redshift range from maybe 0.3 to 2 or so. So they are quite complementary in that sense. So now moving on to the growth of structures. So growth is typically, it's a competition between matter falling in, right, through gravitational pull, and on the one hand, and the expansion of the universe driving stuff apart, right? And this competition is, can be expressed by this equation here. And you can solve this, and then you find how perturbations in density grow as a function of time. This is parameterized here by this growth factor D. And if you take a derivative of this growth factor, you obtain the growth rate F. And this growth rate so tells you how quickly stuff is becoming larger more and more massive, right, as a function of time. And this is very sensitive to models of dark energy or modified series of gravity, which might mimic the same lambda CDM background expansion history. So we might measure the same Hubble parameter, but structures might grow differently. And this plot here is a demonstration of that fact. So here you have two different models. One is Einstein de Sitter, where you only have matter in the universe, and the other one is lambda CDM, so a combination of matter and dark energy. And you see here snapshots from the simulation at different times. And I think this is supposed to roughly give a similar amount of structures today. But you see here, in order to arrive at similar structures today, you need to start with much more structure in the early universe, in the lambda CDM universe, because dark energy is suppressing the growth of structures, right? So this gives us a handle on measuring this thing. And so how are we doing this? Actually, this is where these redshift-space distortions come in that I mentioned at the beginning. And redshift-space distortions are induced by the peculiar velocities of the galaxies, which distort the redshifts that we measure. And this is what this could look like, for example. So imagine there's a central overdensity here, and there's some galaxies around. And since they are attracted to the central overdensity, they will start to flow in. And if we, as an observer, are sitting down here and we look at this structure, then the peculiar velocities, they will make this galaxy, which is behind the overdensity, will appear a little bit closer to us, whereas the one in front will look a little bit further away. And so these structures, which are originally spherical, in the space that we make our measurements in, they will actually appear squashed along the line of sight. Right? And this happens typically on large scales, and this is known as the Kaiser effect. And this can be seen, for example, in this plot here. This is, again, a plot of the two-point correlation function, where you can see on these large scales that these structures are squashed together, right? This is why we want to try and measure the anisotropy of these correlation functions. On smaller scales, where you have formed halos and galaxies are orbiting the center of the halos in on some orbits, this effect of the peculiar velocities leads to a stretching instead of structures. And this is what we call the finger of God effect, because these structures seem to be pointing at us, the observer. And again, this is a signal that you can pick up in the measurement of the two-point correlation function, where you can see here this elongated structure on very small scales below scales of 10 megaparsec. Okay, so here also some constraints from recent galaxy surveys. This is a combination of the growth rate and the amplitude of clustering on scales of 8 megaparsec. So this tells us how clustered is the universe on average. This is called sigma 8. And again, as a function of redshift. And the prediction here, again, in the black line, this is from Planck, assuming a lambda CDM universe. And you can see that the agreement is pretty good, actually, with Planck. We don't see any discrepancies here. But again, this is going to get very exciting in the next couple of years, because with the upcoming surveys, the error bars on these growth measurements are projected to shrink by a factor of 4, and they will span a wider redshift range. Okay, so we will really make very detailed tests of this growth function, and then use that to constrain dark energy and so on. What has become more popular in recent time is not to consider these two different effects separately, the BAOs and this redshift-space distortion signal, but rather try to predict the full dependence of the two-point correlation function or the power spectrum as a function of various cosmological model parameters. Right? So these could be densities of matter, of the baryons. It could also be the mass of the neutrinos, right? The spectral index, so the slope of the power spectrum, or the amplitude. Right, and we can use all these parameters and forward model or predict what the 2-point functional power spectrum should look like and compare that directly to the measurements. And by doing that, constrain or infer what are these parameter values. And in order to do that, there have been various developments on the theoretical side, with the so-called effective field theory models being the state of the art. And I will go a little bit more into detail later on. But what is really crucial here is that we will have very, very good control of our theoretical models, because any mismodeling, right, anything that we don't properly include in these models and don't properly understand, might then lead to biased inferences of these cosmological parameters. So we really need to do very detailed tests of these models against simulations as best as we can do to understand on what range of scales we can actually apply these theoretical models. And right here, I'm just showing one recent example that I was involved in as well. This is analysis of the BOSS and extended BOSS galaxy surveys, where we've put constraints on the neutrino mass and the equation of state parameter of dark energy, right? So this is just meant here as an example of what can be done with these type of analyses. Okay, so, but what I've shown you now, this is sort of the state of the art, right? This is also how we will analyze DESI and Euclid data. But how can we go beyond that, right? To make even more precise measurements of dark energy, modified gravity of neutrino masses, and also maybe to probe what are the physics of the primordial universe, what happened before or in the very early phases of our universe. And there are various ways of making even better use of that data. One of these is to try to probe smaller and smaller scales. And this is what I've called here accessing the nonlinear regime, because on smaller and smaller scales, the growth of structure leads to higher, to more and more nonlinearities, which are challenging to model. Okay. And this is where typically these EFT, these effective field theory methods that I've mentioned on the previous slide, they start to fail. They are more limited to larger scales where these nonlinearities are not yet so large, right? Where fluctuations in the density haven't grown yet to large values. And so to probe this nonlinear regime and to make robust estimates of cosmological parameters, this could be done, for example, with n-body simulations, right? So you would run an n-body simulation, then you have to populate these simulations with galaxies, and then you can measure statistics like the 2-point correlation function or the power spectrum, and build so-called emulators of these measurements as a function of the cosmological parameters. Right, and then you use these emulators to again compare these models with the measurements and infer parameters. Now, there are a number of caveats, I think, related to this approach. And this is, on the one hand, the accuracy of such emulators will be limited by the size of the simulations. Right, there's going to be sample variance in the simulations. And so they are limited by the number of simulations that are available. And since they're typically very expensive to run, that puts a limit on how accurate these emulators can be. Then another point to mention here is that in these cases of this approach, we will have to rely on some prescription of how we put the galaxies in the simulation. Right, so this will impose some strong assumptions. Then maybe one could also say that in the going to smaller and smaller scales, one will eventually get dominated by shot noise, so by the number of observed galaxies. And finally, on small scales, and this is probably very important, there will be galactic feedback effects that are not included in these simulations, right? At least if you just look at dark matter simulations. And so this is not very well understood, right? And the question is, how would one fold that in to make robust estimates of parameters? So an alternative to going to the highly nonlinear regime is to use different statistics, right? We can use statistics beyond the 2-point function or the power spectrum, which were, if you remember, just relying on 2 points, right? Pairs of galaxies. So we can go to larger number of galaxies, and I'll show you a demonstration why that might be useful for extracting additional information. That is, it's useful to know that the power spectrum is roughly proportional to the amplitude of these Fourier coefficients, which means that the power spectrum is not sensitive to the Fourier phases, right? Because you take the amplitude, so phases are gone here. So what does it mean? Here is, I've just taken a slice through an embodied simulation, right? So you see the large-scale structure, right? And what I'm going to do now is I will Fourier transform this field, right? So I have access to the Fourier coefficients, and then I will simply replace the Fourier phases with something else, and then transform back, right? And this is what that could look like, for example, right? And these two fields, even though they look extremely different, they, by construction, have the same power spectrum, so the same 2-point statistics, okay? So we will, using our standard methods, we cannot distinguish these two fields. So, and this is the motivation for going to higher order statistics. There could be higher order endpoint functions. So, for example, instead of counting pairs, you count triplets or quadruplets and so on. You can also define different objects. You can work with, instead of working with galaxies directly, you can work with voids. Would be another way. One can use weighted correlation functions, wavelet transforms. There are many different possibilities here. What I will focus on for the rest of the talk is the use of 3-point statistics. And here's just a quick overview, again, similar to what I was showing earlier for 2-point statistics. And in 3-point statistics, we count triplets, right? So in configurations that depend on 3 different pair separation scales, R1, R2, and R3. And again, in Fourier space, there's an analog. This is what we call the bispectrum. This is now the correlation of the Fourier space density at 3 different wave modes, K1, K2, K3. So let me give you an idea of what such a measurement might look like. This is what I've done here. There's here again like slice from an embodied simulation, and here I'm showing such a measurement of the bispectrum in Fourier space. And what I'm actually showing here is not this bispectrum directly, but something that I call the reduced bispectrum, which is the ratio of this bispectrum divided by products of the power spectrum, and then averaged over one of these 3 triangle sides. And so what you can see here in this plot on the x-axis is the ratio of the 3rd triangle side over the 1st and the 2nd over the 1st, so that in different parts of this plot, you have different triangle shapes, right? So in this, in the top right corner, you have equilateral triangle shapes that you're probing. Here in the bottom, you have so-called folded configurations that are like together. And up here, this is what we call squeezed triangle configurations. And so something is very obvious from this plot, or quite striking, is that you have an increased amplitude here for these equilateral shapes. And the reason for that is that large-scale structure is very filamentary, right? So you see that you have these dense clusters of galaxies, but they're connected through these filamentary structures. And so this is really what we are picking up by a measurement of this bispectrum. So we're really measuring the complex shapes in the distribution of galaxies. So what are the benefits of doing that? Just to recap this. On the one hand, we have more information, so more signal to noise that we can obtain by making a measurement of the bispectrum. Here, this is just for illustration. This is the signal to noise in the power spectrum and bispectrum shown as a function of the maximum K-mode. So on the left-hand side of this plot, you have only large scales, and then towards the right-hand side of this plot, you include smaller and smaller scales. And you can see how the signal to noise grows. And eventually, so you see that the signal to noise of the bispectrum initially is pretty low compared to the power spectrum, but it grows faster as a function of this maximum K-mode than the power spectrum, and eventually might even become comparable. So this is the information that we want to extract. Then another very important point is that these higher order statistics, they're able to break degeneracies in your model parameter spaces. And here I'm showing an example again. So the power spectrum, for example, is sensitive to this combination of the growth rate and sigma 8, for which I showed measurements earlier. And since it is only sensitive to this product of the two, you cannot measure these two things independently from each other, right? Only the product. However, the bispectrum depends on a different combination of these two parameters. And so by combining the two statistics and analyzing the data together, you can separate the effects of the growth rate and this sigma 8 parameter, right? And break that degeneracy. And similarly, something similar happens also for constraining the matter or matter halo and galaxy connection. That is also very critical because that induces a lot of strong degeneracies in measurements of 2-point statistics alone. And so by adding higher order statistics, we can make our analyses much more robust. Then another point is that also 3-point statistics are a direct measure of what might be going on in the early universe. There might be processes in the early universe that generate 3-point statistics, not just through gravitational evolution, but there might be some inherent signals induced by this phase that we call inflation. And 3-point statistics are a direct measure of these things. And these signals, they are preserved all the way in our current universe. So this is really a direct window looking in the very earliest phases, which I find very exciting. And finally, this is more specific to 3-point statistics. I think 3-point statistics in particular are the most straightforward extension beyond these 2-point statistics, because they don't require any definition of new objects, such as voids. There are no additional transformations of the data needed, and they are predictable using perturbation theory methods on sufficiently large scales. So now, if you look at the recent literature, there have been a number of analyses of the BOSS survey, so the CMAS and the LOSI samples, and with using different models. I don't want to go into these details, but the gist is that they found about a 10 to 15% improvement on some cosmological parameters by including the information from the bispectrum, from this 3-point statistic. Right, so you might be now, after everything that I told you so far, you might be a little bit disappointed. You go through all this effort, but at the end of the day, you get 10%, 10, 15% improvement. I mean, this is great, right? No doubt about that. But maybe is not as much as one might have hoped. And so what's the reason for that? In these analyses, they have to impose fairly conservative scale cuts. So they have to restrict the analyses to fairly large scales, because what they observed by testing the performance of the models against simulation data, that these models, they break down, they fail fairly early on when you go to smaller and smaller scales. And in order to prevent any sort of biases, you just cut the range of scales over which you make the analysis, and that limits the amount of information one can extract. And the scale at which they cut these measurements are 0.08 H inverse megaparsec. Not quite sure what that would be in megaparsec scales. But I think the comparison here is interesting, because without these redshift space. So in real space, we have shown that models, or these models can be used up to scales of 0.15, so twice as large as what this scale curve would shows. And so maybe the reason for this breakdown of these models is related to the transformation from real space to redshift space, so by the inclusion of these peculiar velocities of the galaxies. And so maybe this is a point one can try to understand a little bit better, and that's what I will tell you about now. And for that, we have to dig a little bit into how we are modeling our clustering statistics. I will spare you most of the details, but just to give you a little bit of a flavor of what's going on. So first of all, why is this challenging at all, right? And this is something I've mentioned throughout the talk already. There's gravitational collapse happening that makes initial fluctuations grow, right? And in the CMB, fluctuations in temperature were of the order 10 to the minus 5. Nowadays, these fluctuations have grown by about 5 orders of magnitude, right, through amplification of the collapse process. And that makes this so challenging, because while we could analyze CMB measurements with linear theory, this is no longer possible for large-scale structure, right? Because we have to account for nonlinear evolution. We also have to account for what we call galaxy bias. Galaxy bias denotes the relation between dark matter, the matter structures, and the observed galaxies, which is also a nonlinear relationship. And finally, what I've mentioned so far already, the redshift space distortions. So the inclusion of the peculiar velocity effect of the galaxies. And again, this is this transformation is a very nonlinear process. So our tool that we use is called perturbation theory, or these effective field series. And the philosophy of that is that on sufficiently large scales, these fluctuations are still small enough so that we can expand the observable density in powers of a linear density, right? As long as the densities are small, these power series they will converge, right? And on these scales, we can apply such techniques. And there has been a lot of effort over the last years to improve these so-called perturbation theory models. And then this is just very schematically what a model for the power spectrum of galaxies in redshift space might look like, you know, with various terms that are not so important for what I will tell you. The only thing I want to tell you a little bit more about is this function d here, which is related to the fingers of God effect that I told you about in the beginning, right? This is the stretching that comes from virialized motion of galaxies in the more central parts of clusters or halos. And that leads to the stretching along the line of sight. And in the power spectrum, that is equivalent with a dampening of the power, okay? And now, why is this problematic? Here, what you need to know is that the mapping from real to redshift space does not depend on just the velocity field itself, but it's the difference between the velocities at 2 different positions. And so what I've plotted here is, as a function of position here, right? This is the line of sight velocity component, and I've split this into a large scale component in blue and some small scale component, right, that varies much more rapidly with position in orange. And here you have, you can imagine 2 galaxies separated by some distance r. And you can see that if we take the difference of the velocities at these 2 positions, the large scale component of the velocity difference will always cancel out, because it's the same at the position here and that position there. So what we are left with after taking the difference is only the small scale part of these velocities. And that makes it so challenging to model, because what we can only hope to model with these perturbative methods are the large scale components, right? Because they tend to be small, but the small scale fluctuations, they're not. And And that's why this is is pretty challenging, and this has been known for a long time. Actually, here you can see the distribution of velocities, of line of sight velocities, as a function of different separation scales, going from very small scales here, 0.1 megaparsec, 5 megaparsec, and then very large scales, 200 megaparsec. And what you see is that even on the very larger scales, this distribution of velocities never becomes a Gaussian. This is what we would expect if it's not sensitive to these nonlinearities, right? But what you see instead is that these distributions have very strong tails, right? They don't fall off as quickly, and this is induced by these nonlinearities. And we hope to try and see if we can include that in our models. And here I will just try to give you a schematic of how we try to do that. Here is, I've written the model of the power spectrum, which is given as some integral of the two-point correlation function in real space. And then it's convolved with some function that we call this the moment generating function of mass-weighted velocities. Okay, sounds complicated. You don't need to know what the details are, but the thing that I want to point out is that you can rewrite this part of this equation into a component that depends on the galaxy density, and a part that does not, right? A part that only depends on peculiar velocities. And you can apply perturbative methods to this part, because anything that depends on the density, there we have access to this perturbative methods, because we have we can guarantee that some of these parts can be are small and can be expanded, whereas this part here, this is very sensitive to nonlinearities. And so now there are two different choices for how this part is being modeled. The effective field series, or EFT, they choose also to expand this thing perturbatively, even though that might not be very applicable. And then what we've been looking at, also with Martin and Benjamin here in the audience, we have tried to come up with a more non-perturbative description of this function here. And this is what we try to compute in some limit, and this results in some damping function of the power spectrum that models this finger of Lord effect. And okay, so this is the defining difference between these two models. And what I want to do now is to compare how well we can model measurements of the power spectrum within this EFT and this VDG model. VDG stands here for the velocity difference generating function. Okay. Okay, so for testing this performance, we need some test data. And here's where we rely on simulations, where we know what is the underlying truth and where we can check whether we can recover correct parameter values from our models. And this here we use the Minerva simulation suite, which consists of 300 simulations, 1,500 megaparsec per site each. And then they have been populated with these with galaxies using some prescription, some halo occupation distribution model, and that has been tuned to match the clustering of the CMAS galaxies from BOSS. And then what we do is we extract measurements of the power spectrum and bispectrum in multipoles, which means that we're no longer splitting the measurements into components along the line of sight and transfers to the line of sight, like I was showing you initially in the beginning of the talk. But these anisotropies are projected into Legendre multipoles, so different moments of this anisotropy, right? The monopole here in blue, this is the measurements of the power spectrum multipoles as a function scale. The monopole is simply the average over all lines of sight. And then we have here a part this is called the quadrupole, and finally the hexadecapole, which quantify different parts of this anisotropy. And then what we assume for inferring parameters from these measurements is that we have to make some assumption for the measurement errors. This is something that we predict using some Gaussian assumption, and we tune these error bars to something that is that we would expect for Euclid, for Euclid, for one redshift bin of Euclid, centered at a redshift of 0.9 with a thickness of the shell of 0.2 and covering the footprint on the sky that Euclid will observe. Okay, so here, this is what the outcome of such an analysis, this likelihood analysis, might look like. So this shows posteriors for the different model parameters. And in particular, I'm showing here in the top part of this plot, these are the cosmological parameters that we have varied in these analysis. This is the Hubble expansion rate here. In the first column here, this is the matter density, omega c, and then the amplitude of the power spectrum here. And for this, we make use of a fast code that we've developed with Martin's group called COMET that allows us to make many analyses of this data, play with different setups, different parameter combinations, and in particular different cuts of the data, right? So we vary the range of scales over which we do this analysis, right? You know, starting with fairly large scales. So in this case, I'm showing here the cut was 0.2 H inverse megaparsec. And what you can see here in blue is the EFT model, and in red is this so-called VDG model, right? The one with the non-perturbative treatment of peculiar velocities. And you see that in this case, at this cutoff of scales, there's a very good agreement between the posteriors. We don't see much of a difference. But if you now increase that cutoff, you include more and more of the small scale regime, you start to see differences appearing between the two models. And you can see, for example, how the contours, so the posteriors of this EFT model, they start to shift away from the fiducial values of the simulations, which are indicated by these dotted lines here. Okay, so the inference of the parameters with that model, they become biased if we include the small scale part of the data. Whereas with the VDG model, we recover the correct values of the simulation. And we can do this a little bit more quantitatively, right? So I will now show you plots that are shown as a function of this Kmax, so the cutoff scale in these analyses. And what I'm plotting here in the top panel, this is what we call the figure of bias. This is something that you can imagine how much do the posterior mean values differ from the underlying truths in a three-dimensional parameter space. Then there is a measure for the goodness of fit, a p-value, and finally what we call the figure of merit. This is the size of these ellipses that you saw in the previous plot. So if they shrink, right, we have more information, right? The constraints on our parameters are tighter. So we want larger figure of merits. And yeah, in this plot, then I'm comparing this VDG and EFT model. And you can see as we go to smaller and smaller scales towards the right-hand side of this plot, you can see how this EFT model eventually becomes biased, right? It returns incorrect parameter values, whereas over this whole range of scales, the VDG does not, right? It still recovers the truths. And you can see how this translates into much tighter constraints, because if you compare the figure of merit at the scales where the model starts to fail, right? Maybe one of these values here for the EFT model, whereas you can go all the way up here for the VDG model. So this is maybe a factor of, well, not quite, I don't know exactly how much it is, but 60, 80% or something like that. So this is very encouraging. And now let's add the bispectrum into this analysis as well. I will take this fixed scale cut for the power spectrum that I fixed to this scale of 0.3 H inverse megaparsec. And then I do the same game, but now including the bispectrum, and where the x-axis of this plot is now showing the cutoff scale for the bispectrum data. And here we have the same panels, figure of bias, p-value, figure of merit, and in addition, there's a panel that measures the tension between the posteriors of the power spectrum alone and the combination of the power spectrum and bispectrum. And we see here, again, a very similar picture. The EFT model eventually becomes biased if one goes to 2 small scales, whereas in the case of this VDG, there's no such problem occurring. And you can also see this quite nicely. There's a strong tension that you get between the joint P plus B and P alone, whereas this tension is not there in the VDG model. And so this is consistent what previous studies have done, because they limited their analyses to these scales here, right? So 0.08 roughly, where the model was doing fairly well. But with this VDG, we might be able to go to scales to smaller scales. And I should say that this is shown exemplarily here for the CMAS sample, but we find very similar performance also for other galaxy samples like LOSI, and also for the Euclid flagship galaxies that Benjamin has been testing. And now for my final slide, I just want to give you an idea what where are we actually gaining from the bispectrum, and how much do we gain compared to the 2-point statistics only analysis from the power spectrum. And for this, I've split the same plot from last slide into the bispectrum monopole only. So this is the first multipole moment. And then in red, this is what was shown on the previous slide. This is the combination of the bispectrum monopole and quadrupole. And if you now look at different scale cuts here, this is 0.1. This is what previous analyses have used. You see the improvements over the power spectrum here for the different parameters, cosmological parameters that we've varied. So H, the matter density, and the amplitude of the power spectrum. And you see that in H, there's nearly no improvement from adding either the bispectrum monopole or both, monopole and quadrupole. There's a bit of improvement in the matter density, and again, nearly no improvement in the amplitude of the power spectrum. However, that situation changes quite dramatically when you go to these smaller scales. Right now, you see that there's about 20% improvement in the expansion rate, 50% reduction of the error bars in the matter density, and about 30% in the amplitude of the power spectrum, where we see that the monopole mainly improves the constraints on H and omega C, whereas the quadrupole helps in tightening the posterior for the amplitude. This is mainly due to a better or stronger breaking of the degeneracy between the growth rate and sigma 8 by combining the power spectrum and bispectrum, like I mentioned earlier. Yeah, and with that, I want to finish. So the things that I want you to take away from this talk is, first of all, in order to maximize the capabilities of upcoming galaxy surveys, I think it's very critical that we try to exploit higher order statistics. And in particular, the 3-point function or the bispectrum is the most accessible of those various possibilities of extracting that information. Then I've shown you that perturbation theory is a very powerful and accurate tool for analyzing this data, at least if we apply it on scales where we can trust these models. And tools such as Comet, the theory emulator that we developed, drastically simplifies testing these models and figuring out over which range of scales we can apply these models. And then finally, I've shown you that some insufficient modeling of the mapping from real to redshift space, including peculiar velocities of the galaxies, can limit the gains we might get from 3-point statistics, right? And some non-perturbative treatment of that damping function boosts the returns from the bispectrum, can lead to pretty big improvements. Yeah, and with that, I would like to thank all of you for listening. I think now it's close to pizza time. And also thanks, of course, to my collaborators, including Benjamin and Martin here. So thanks.
Thank you for the nice talk. Time for questions.
I'm interested about the flexibility of the non-perturbative description of the peculiar velocities. because when analyzing aerodynamical simulation, what you find is that depending on the different type of tracer that you use, the galaxy population, the velocities are different. And for example, for the CMAS sample, the peculiar velocities of satellites are quite different from the distribution velocity for the dark matter particles.
Yeah.
So when you populate a simulation with an HOD, typically what you do is to put the velocity field that you measure from the dark matter. So my question is, have you checked different ways of putting the velocities there, following something that is more closely to what you measure in the aerodynamical simulation? So you know that the function is very flexible, can describe different types of tracers and so on.
Okay, so what we've done so far is only tests on HODs, right? So where I guess you have the same way of putting velocities of the galaxies, right? Deriving from the velocities of the matter particles. And something that changes though with the different HODs that we've looked at is the satellite fraction, right? And that induces differences in the velocities, because if you have HODs that are mainly a catalog that is mainly dominated by central galaxies, they're not moving that much, right? So the impact of this is small, whereas if you have a sample that has a high satellite fraction, the impact might be much stronger. We only see from these different samples that the difference between the two models is consistent. So with this treatment that we've used so far of the damping function, we get a better modeling. But I think it would be very interesting to apply that to other samples, for example, subhalo abundance matching techniques, right, and see if the same holds true there as well. That is something we haven't done, and I think it would be exciting to do that. Because it's true that the model that we use for this damping function is still fairly simplistic, and it can be improved, something that we're actually working on as well. And these tests would be helpful.
Potentially with the benefits of using the high order statistics. So, what's the reason why signal to noise is greater using high statistics at small scales in comparison with supernovae statistics? And also why you can study remote non-Gaussianities with high order statistics and not with supernovae?
Right. So the first question, why you get this increase of signal to noise with 3-point statistics, is because when you count pairs versus triplets, at some point you have many more triplets than pairs you can count, and that leads to this increase of signal to noise compared to 2-point clustering. It is maybe a little bit exaggerated what I was showing you, because the plot that I was showing was based on a Gaussian covariance matrix that is not taking into account the correlation between different triangle configurations. If you do that, you will see a flattening of the signal to noise, right? Also for the power spectrum, it happens there as well. But that eventually will limit the amount of information. But the steepness, it is induced by the higher number of triplets. And the second question was why you can extract something about the primordial universe with 3-point statistics. This is because there might be processes in inflation that generate an inherently 3-point bispectrum signal. And there is a way of probing that with 2-point statistics, but it's an effect that occurs in the galaxy bias. So what happens is that you have a higher galaxy bias on very large scales in the power spectrum. But the problem there is measuring the signal is very tricky, because on very large scales, you have to deal with a lot of systematics in the survey. Right? So accessing that information is not as straightforward. But with the bispectrum, you have the signal of of inflation, right? It occurs on all scales. Okay, that makes it a little bit more straightforward, I believe, to extract that. Even though there are, of course, other challenges related to the spectrum. But yeah, that's the gist.
Maybe last question.
So thanks a lot for the nice talk. Let's get a small question. So touching on what you said about the information gain for the bispectrum. So I was wondering, in the analysis that you showed for the constraints when you combine power spectrum and bispectrum, you use a Gaussian covariance matrix also for the bispectrum.
Yeah.
Okay. So can you say what happens if you include something that deviates from this approximation, which I guess it's only strictly valid when you have large range or you have a lot of short range?
Yes. Yeah, maybe I can first of all show you what the comparison looks like for the Gaussian covariance, because we can measure the variance from our 300 simulations. And since we don't impose any survey mask, the Gaussian approximation is typically very, very good, right? So the survey mask will induce correlations. But in this setup that we had here, this is not so relevant. What you see here, this is the power spectrum covariances, different components, multipoles, and cross-correlation of the multipoles compared to our Gaussian model, which gives very, very good agreement over the whole range of scales that we are including. And similarly, this is what we find for the bispectrum. This is now here shown a bit, it's a bit of a complicated plot because this is shown as triangle count. But so just to give you an idea, this is sort of the range of triangles that we include in the analysis that I've shown you. And this is for the monopole, quadrupole, and the cross. And you can see with this Gaussian model, we reproduce these measurements very well. With, I think, the vast majority of these triangle configurations, they have an error of less than 10%. And that means that the effects of the non-Gaussian covariances, at least on the scales that we consider, is not that big. Here I'm showing only the diagonal of the covariance. Of course, the non-Gaussian part will also induce correlations between different triangle configurations. But also there we've checked that there's only a minority of configurations that have correlation coefficients larger than 30%. So it will somewhat reduce the gains from the bispectrum if you include that, but I think not qualitatively.
Okay, well,
Yeah.
very
Sure. Very quickly, would it make any sense to go to the 4-point correlation function? So then the improvement would be 1 or 2%. What do you expect?
Yeah, it's a good question. I mean, also there have been some measurements in the literature. It's not that this hasn't been done yet, but it gets more complicated, right? The modeling will be even more sensitive to nonlinearities. And another issue is that you've seen the comparison of the signal to noise power spectrum versus bispectrum, with the bispectrum on large scales being lower compared to the power spectrum. That trend increases the higher you go in this order. So for the trispectrum or 4-point function, it will be even lower at large scales where you can model these statistics, right? So you only gain if you reach a point where the signal to noise is sufficiently large, and that might be tricky to achieve with the trispectrum. That is my feeling. I think, well, maybe it will get explored, but this is would be my intuition. It would be very difficult, I think.
Okay, then let's thank the speaker again. Go for a pizza.